All right, Ben, thanks for the introduction. So, as Ben mentioned, today we are going to talk about a P4-Enabled OVS. That is how we added support for P4 in Open vSwitch. So what we mean by that is a switch that has a P4 DSL at the top level language that you can write your programs in, and then it compiles down onto Open vSwitch. So before talking about the compiler and the details of it, I would like to go a little deep into the architecture of Open vSwitch itself to sort of like try to find out like what were the areas that need to be specified in a high-level DSL, because OVS itself is a software switch, so there are different components that you can write in the software. But from the standpoint of a protocol designer, what was the necessary things that he needed to program, and what were the extraneous informations that were there in the switch that they don't want to consider when specifying a switch? So in Open vSwitch, it consists of two main parts. First is the packet I/O. That is, when a packet comes in, you need logic to take it as to receive the packet interface and then send it out to the packet processing logic and then to the egress. So normally the packet I/O is actually implemented using kernel or DPDK, and then there is the packet processing logic that sits on top of it to process the packet. In OVS, it's usually implemented as a parser with a match action pipeline. And then there are complex APIs for different packet and I/O interfaces, like for kernel, DPDK, and so forth, that you build your packet processing logic on top of. So the question is, like in OVS, as a network programmer, I am only interested in specifying the parser and the match action pipeline. That is what I describe my program in. I do not have to understand the complexities of the underlying packet I/O, that is DPDK or kernel. So think of it. You are a network programmer. You know how to write RFCs, build protocols, specify a pipeline. But then the thing is, like, once you have this sort of like the idea about a new protocol or the RFC that you have written, now you have to implement that. So how do you do that? So for that, then once you start building the switch, you find out like, okay, there are these things like kernel, DPDK, netmap, and so forth. First, you have to understand them before you can write a fast, optimal switch that can run your protocols or RFCs. So the question then was like, how do we make it possible for a network programmer to quickly specify new protocols without understanding or dealing with these underlying packet IOs? So from the diagram, maybe it's obvious, but you can think of like in terms of the OVS source code, the entire source code, it was quite hard to first of all find out the nice boundary to split the packet processing logic with the DPDK part, because there is a huge, there are different running components in OVS, like the command line APIs, the controller interface, the match action pipeline, the flow structures that they have, and so forth. So after spending some time, we found out like, okay, we can actually build up a nice partition between the packet processing logic itself and the I/O. So what we did, we separated the packet parsing part and the match action pipeline from the switch itself, specified that using a DSL, and then wrote a compiler that takes that DSL description and then generates the necessary parser and match action pipeline code for the OVS. In this work, we use P4 because we have seen in the past couple of years, match action pipeline seems to be sort of like a canonical or a de facto standard now for expressing pipelines. Network programmers feel comfortable to express a pipeline as a sequence of match action tables where they match on a certain field, and then they have certain actions that act on the packet. The only thing they needed more to sort of build up a programmable pipeline was to specify a parser, like how to express new headers, how to extract them, and then feed them into the match action pipeline. So previously in SDN, like using OpenFlow and so forth, they had to stick with what was already being parsed for them based on a given OpenFlow interface, but now they can actually express their own headers and protocols and then extract the necessary fields and then run them through the match action pipeline. So P4 is an open source language. There's a lot of effort going on in people in making it better and adding more support in terms of the different architectures they can support, the features that they need to provide in the language itself for the network programmers. So, but in the hindsight, like what P4 does, it gives you the ability to add new packet headers and fields, specify metadata like input port, registers, and so forth, a parser to parse the fields from the packet, and then there are actions that you can run on the packets itself. And then, and then there is a set of match action tables that have a match part that match on a certain field, certain actions based on a match that are applied on the packet, and then finally a control flow of these match action tables. So unlike being a linear match action pipeline, sort of a DAG, it's a DAG with that can actually lead to help implement arbitrary control flows rather than just a linear control flow. Okay, so after doing this separation, the first thing that we did was again, in the beginning we talked about we wanted to make it easier for a network programmer to specify their logic. What that means is like they should not deal with underlying sort of code that is necessary for interacting with the packet IOs for DPDK and kernel. So what we found out, like just specifying the packet processing logic for the native OVS that was there at the time in the master branch, you just needed 341 lines of code, similar to what Nick McEwen said yesterday. But doing the same thing in the C code, like the underlying open vSwitch code base, you had to touch like thousands of files, like 14,000 of lines of code to actually specify the same change. So what we did, we came up with this compiler that automates this process. Given these 341 lines of code, it generates these thousands of lines of code for you automatically because there was a certain, you can automate this process for a larger part of the OVS code base. Okay, so moving on. So the problem now was, so given that you can express your program in P4, and then the question was like, how do you compile that program to OVS? So in terms of compiler, what this means is like, you are writing a certain program for a given forwarding model. Like you're writing in a P4 program with an assumption that this is how the underlying architecture looks like, and this is what I'm expressing to run on that architecture. But that is the P4 forwarding model. That is not the actual forwarding model that OVS supports. So the problem then is like, how do you take this forwarding model and then map it down onto the OVS forwarding model? So I'll talk a bit in detail about what these two models are. So once you're doing the compilation, then there is some inherent performance overhead because these two are different models, and you're sort of like bridging the gap between the two. So there are certain redundancies, and then we implemented some optimizations to remove those redundancies. So first of all, I'll talk about the P4 forwarding model. In the P4 forwarding model, we have a packet parser that parses the packet. So first of all, it identifies the packet headers, make a copy of the headers as header fields, and then there's a checksum verify that verifies the checksum, a match action pipeline that operates on the headers, a checksum update that updates the header of the packet itself, and then finally a packet deparser that writes the headers back onto the packet itself. So this is what the P4 forwarding model looks like. You can specify the control flow in the match action tables, specify the header structures, and then the packet parser, and so forth. And the thing is, like, because we are applying the changes on the actual packet at the very end of the pipeline, we call this model a post-pipeline editing model. But in comparison to OVS, what we have is we have a packet parser running in the fast path. The packet comes in, we identify the fields, we look them up in the match action cache, and then once we see a miss, we go to the match action tables. This is the control flow of the pipeline in OVS. After running the packet through the match action tables, we write a flow rule, and then the packet goes out to the egress. Similarly, when next time the packet comes in, you again identify the headers, and now if the header packet belongs to the same flow, then it will see a hit in the match action cache. And then the packet will go through egress rather than going through the match action pipeline and then spending the time in generating the rule and so forth. So this is what the OVS forwarding model looks like in comparison to the P4 forwarding model. And because the changes were being applied on the packet directly rather than keeping a copy of the headers, so we call it inline editing model. So in order to compile P4 to OVS, we modified OVS in certain aspects. We added some missing components, such as checksum verify, checksum update, and packet deparser. And then, in order to enable both the model, inline editing and post-pipeline editing. So now the problem comes down to how can we take the P4 forwarding model and then compile it onto OVS. So you can see there's a naive mapping where you can just take the parser, convert that into a parser in OVS, match action tables to match action tables and so forth. But we found out like the default packet forwarding model that P4 has a lot of overhead. Like there are a lot of redundant computations that are happening in there. So for example, in the case of checksum verify, you do the checksum on the entire packet. And in the case of checksum update, you are again doing the checksum on the entire 12 IP fields, whereas you can do in software those checksum in an incremental fashion. So the compiler can actually learn those aspects and can sort of produce a more optimized implementation rather than going with the default one that the P4 forwarding model gives you. Okay, so far I talked about like OVS as having a match action cache, but it's actually two caches. One is the Microflow cache, and the other is the Megaflow cache. So for the evaluation that I'm going to show, we actually disabled the Microflow cache. And the reason being, the Microflow cache was sort of like a fixed function cache that was relying on the hash that was computed by the NICs themselves. And the NICs only know about the 5-tuple. Right now, we don't have the capability to express arbitrary header fields in the NIC to generate a hash. So that's why we sort of, again, the whole reason for this work was to be protocol independent. So for now, we just removed the Microflow cache from our evaluations for both OVS and PISCES. And later on, Cian is going to talk about a software Microflow cache, which is a programmable cache, and then how it helped further improve the performance. So we took a naive sort of a program. So we took a simple program, which was a router with access control list, and then we compile it onto PISCES using our compiler. And we found out like the naive implementation where we just do a one-to-one mapping, there was a 40% performance overhead compared to the native OVS implementation that was there in the master branch. We found like there are multiple reasons. There are two main reasons why this was happening. One was the CPU cycles per packet that we were consuming in the pipeline, and then the cache misses, like how often the packet is going to the slow path. So for the CPU cycle, we found out for the sample application that we used that the parser was taking 76.5 cycles for the PISCES case, whereas it was taking 43 cycles for the native OVS case. Similarly, for the cache match, the difference was not that much, but the primary difference was between the cache actions. Like we were taking roughly 3 times more cycles than the native OVS. So there was some opportunities of doing optimization here, and this is what we did later on. And the throughput was like 7.6 gigabit per second for PISCES versus 13.5 gigabits per second for the native OVS. So again, we did some further study to find out like what is it that is actually affecting the CPU cycles. And then what we found was that there was like we were doing extra copies of headers in P4. The forwarding model assumes that when a packet comes in, you identify the headers, you make a copy of them, and then you pass them through the match action pipeline. So that was consuming some cycles. And then we were specifying the checksum fully. That means like when a packet comes in, we take all the 12 fields, do the checksum verify. And then at the end of the pipeline, after, for example, we just modified TTL, but still we were doing a checksum on the entire header, like taking all the 12 fields and running the checksum over the entire header, rather than doing it incrementally for just the TTL. And then finally, there was this other thing that we were able to do with P4 because we knew what header fields are being touched in the match action pipeline. So based on that, we were able to remove the fields from the parser that were no longer being used. So for example, if we have a switch, and the parser is actually extracting layer 3 fields, those fields are not necessary. So using some program analysis, we were able to remove them as dead code from the parser to save more cycles. So this is a chart of all the optimizations that we did. I wanted to go through all of them, but due to time limitation, I thought like maybe I should just give a series of like how the performance improved by each optimization that we applied. So we started with the inline versus post-pipeline editing, where the compiler found out like, okay, whether the post-pipeline editing mode is suitable or inline editing mode is suitable for this particular program. And then we used incremental checksum to convert the full-blown checksum into incremental checksum based on the program analysis of the program, like what fields were actually modified in IP. And then based on that, only apply checksum to those modified fields. And then there was parser specialization to remove the dead code in the parser, action specialization, and so forth. So after doing all these optimizations, we found out like the parser was now taking less cycles than the native OVS for this particular program. We didn't do any optimization for the cache match because the gap was not that significant, and the match part of the Megaflow classifier was already very programmable. And then for the action part, we found out, like, after doing the optimizations, we were performing pretty closer to what the native OVS was doing. So in the end, after doing all these optimizations, we were able to reach the performance of what the native OVS performance was. So the argument that I want to place here is that even though you are compiling in a high-level language, by doing appropriate compiler optimizations, we were able to bring the performance closer to what was already there in the native OVS. So for a network programmer, this is better because now they can express their logic in a high-level language without worrying about the underlying packet I/O and still getting the same performance. So in summary, before it was the performance overhead was 40%, now it was reduced to 2%, which is a huge gain. And finally, the second part was the cache misses, like how often the packet goes through the slow path. So what we found out using our micro benchmarks, that for a very simple pipeline that is only matching on, say, input port and sending the packet to a specific output port, if the packet goes through the match action tables, it takes around 50 times more cycles than if it gets a match on a cache. And we found out, like, even for that very simple program, no matter what the packet size is, you are only getting 1 million packets per second throughput. Whereas if you are running through the cache line, previously you saw in the slides, like, you can go up till 13 gigabits per second. So again, we did some study. We found out, like, there are certain factors that were affecting that we could, like, operate on or optimize for to improve the cache hit rate. I'll not go into the details, but the first thing was to do caching based on low entropy fields. What I mean by that is, like, when you're trying to cache some rules, try to cache rules based on those set of fields that are changing less often in the traffic. Because if they're changing less often, you will get hit most of the time. And similarly, there were certain stateful operations, like decrement TTL and increment TTL. What we found out in there was initially in native OVS, what happens is, like, you convert those stateful operations into stateless operations. So for example, if you want to decrement a TTL, in the Megaflow cache, you will match on the current value of the TTL and then set that to the one less than the value that the packet had. So if you have 64, you will match on the 64 TTL value, and then you will set it to 63. So you can see if the TTL value is not changing very often, you are adding more and more rules in the cache. So we converted that into a stateful operation rather than matching on the changing field. What you do is, like, you actually set that in a stateful fashion in the action part. So based on that, we were able to remove the sort of like the explosion in the number of cycles based on the field that is being modified. For TTL, it wasn't that hard because TTL changes less often, but maybe for TCP sequence number or so forth, that you may end up installing more and more rules in the cache. So at this point, I'll take a stop, and I'll hand over to Cian to talk about the results on the Microflow Cache.
Yeah, thank you, Shahbaz. So I'm going to talk about the Microflow Cache. And as Shahbaz mentioned already, this was disabled in all the performance tests that he did. And my work was in re-enabling this and making it protocol independent. So you can see this is where the Microflow Cache fits into the PISCES forwarding model. So I'm going to talk a little bit about the internals of the Microflow Cache, just so you can get an idea of how P4 affects these internals. So there's three main stages to the Microflow Cache that we're concerned with. The first is the extract field stage, followed by the hash fields. And as was mentioned previously, this is where the 5-tuple of the packet is used. And this is what makes the Microflow Cache protocol dependent. And after the hash field stage, there's a lookup. And this lookup uses the hash calculated in the previous stage to speed up the lookup process. And this is done to figure out what action to perform on the packet. So here you have two possible scenarios. You can have a hit or a miss, where if you have a hit, you carry out your action and the packet leaves the Microflow Cache. If you have a miss, you send your packet to the Megaflow Cache and it gets processed there. So now I want to talk about how P4 changes this Microflow Cache and the internals. So now all three of these stages become dynamically generated, and they're generated based off the P4 file that's input to PISCES. And the most important part of this is that the hash fields stage is now generated. And basically, the user of PISCES can now specify the list of fields that they want to be hashed. And then these are the fields that are hashed. So this is what makes the Microflow cache now protocol independent. So here I just want to show the initial test results that we had in comparing the standard OVS Microflow cache to the PISCES Microflow cache. And here you can see that PISCES performs worse than the standard OVS. And I did some work in trying to figure out why this was the case. And I found some interesting results which kind of led to a potential compiler optimization which can be carried out. So if you look at the slide here, you can see sort of a simplified version of the flow structure that's in OVS. And I'm using a simplified version just to illustrate a point. So in trying to figure out where the performance hit was in PISCES, I noticed that the particular order and the location of headers in structs made a large difference to the performance you were getting. And this is down to the fact that certain structs in OVS span multiple cache lines. And when this happens, depending on which cache line you're in, you could get different performance for your switch. So if you look at this flow here, you can see that the Ethernet header, IPv4 header, layer 4 headers, these would be generated by PISCES based off the protocols which are defined in P4. And here you sort of have a worst case scenario where your Ethernet header is in a separate cache line to your IPv4 header and TCP headers. And this can result in a hit in performance. So if you take a table, let's say, that matches on an Ethernet header and an IPv4 header, this will, if you want to read these headers, you'll have to fetch 2 cache lines from the cache. So it kind of doubles the amount of processing that you have to do in order to perform a lookup on your packet. So what I thought was, you could do some static analysis of your P4 program and see which fields are being looked up together. And then you could ensure that these fields reside in the same cache line. And this would cut down on the performance. And this is something similar to what I did to improve the performance of PISCES. And in my case, it was just a manual optimization. But it kind of shows the potential of how this could be done at the compilation stage and could be an automatic optimization. So here you can see that the performance of PISCES is improved by moving the location of certain fields in the cache line. And finally, I just wanted to compare 2 different PISCES use cases. So the 5-tuple test case, this is the test case you've seen earlier where the 5-tuple is being hashed. And the other test case is the layer 2 address test case where just the 2 Ethernet addresses are being hashed. And here you can see that when you're hashing less fields, you get more performance. So this kind of shows the relationship between the number of fields being hashed and the performance that you get. So it kind of shows the power in allowing the user to specify which fields they want to hash so they can kind of trade off how good they want their hash to be versus how performant they want their switch to be. So that's the end of my part of the talk. So if you guys have any questions for either myself or Shahbaz, we'd be happy to answer them. And thank you very much.